12.3 Lesson 2, Deriving the Position Vector from the Acceleration Vector for an Object in Projectile Motion. The objectives for today's lesson are 1. Given the initial height, speed, and angle of elevation from which a projectile is launched, you will understand how the position vector for an object in projectile motion is derived from the acceleration vector. So in this problem, we will consider that the only force acting upon the projectile after launch is the force due to gravity. So we're going to not consider anything due to air resistance. So we'll neglect air resistance. So objective 2, you will understand that the position vector for an object in projectile motion will tell me the position of the projectile at time t since the object was launched. So we begin with the projectile at an initial height above the ground. It is launched at a particular angle with respect to the horizontal and at a particular initial speed. So let's look at a video demonstration of what we're talking about, and then we will get started with the derivation. You can click on the link on the upper right corner of the screen to go ahead and watch the video demonstration of this particular object that is being hurled, and it goes into projectile motion in a plane that is parallel to the garage door. So as we saw from the video, the object was launched at a particular initial height. So here's the object. I'll go ahead and highlight that so you can see that better. And it was launched at a particular initial height above the ground. So this was the initial height from which the object was launched. And it was launched at a particular angle. And you can see that it was launched at a particular angle with respect to the horizontal. So here is the horizontal. And it was launched at this angle with respect to the horizontal. So this is the launch angle, which we will call theta. And it was launched at a particular initial speed. So we're going to start with the initial height, the launch angle, and the initial speed at which the projectile was launched. So if you combine the launch angle with the initial speed, you get what we call the initial velocity vector, which I can represent like this. So this is, let's say, the initial velocity vector, and the magnitude of this initial velocity vector is what we call the initial speed. So here is the object at a later time. This is where the object is a little bit later. And this is where the object lands. So if we trace the path of the object by connecting these 5 points that I was able to get from my pictures, then this is the path followed by the projectile as it travels through the air in a plane that is parallel to the garage door. So we're going to derive the position vector for the position of this object in terms of the initial height from which the object was launched, the launch angle, and the initial speed at which the object was launched. So our goal is to come up with a vector-valued function that would give us, in terms of the time since the object was launched, the x-coordinate of the object's position with respect to our coordinate system, and the y-coordinate of the object's position with respect to our coordinate system. So what is our coordinate system that we had specified at the beginning of the demonstration? We said that the x-axis is over here at the bottom of the garage door. So that's the x-axis. And here's the y-axis. And of course, this would be the origin. So we're going to have a function that would give us the x-coordinate of the object in projectile motion as a function of time since it was launched, and a function that would give us the y-coordinate of the object in projectile motion since the time it was launched. And x and y coordinates are with reference to the coordinate system that you see here. While I have this, I want to take the opportunity to discuss some vocabulary that you'll be using in later lessons. So, for example, when we talk about the maximum height of the projectile, we're thinking about, okay, what is the highest that the object goes as it is traveling in its projectile motion path. So in other words, you want to find the maximum possible value for the y-coordinate of the object that is in projectile motion. That would give you the maximum height. There's also something called the range of the projectile. In other words, what is the horizontal distance traveled by the projectile from the time it was launched to the time that it lands. So that is called the range. So as we move on to the next part of the lesson, we want to keep in mind that we're simplifying our problem so that we're neglecting air resistance, and we're considering that the only force acting on our object after launch is the force due to gravity. So we start with that. We start with the acceleration vector due to the force of gravity, and then from that we will integrate to find the velocity vector, and then from that we will integrate to find the position vector, which is what we're after. And there are some initial conditions that we know, such as the initial height from which the object was launched, the angle at which the object was launched, and the speed at which the object was launched. And we will use these initial conditions to help us solve for the constants of integration when we integrate the acceleration vector to find the velocity vector, and then when we integrate the velocity vector to find what we're after, which is the position vector. So let's look at our initial conditions. We know the initial height. So the initial height is 0I, because you can see that my projectile was launched above the origin, plus hj, whatever h may be for the initial height. So that's an initial condition that I have. And for the initial velocity, let's do the following. So you can see what we just did now. We took the initial height and wrote that information in terms of a position vector at time is equal to 0. So let's see if we can take the launch angle, theta, and the initial speed and put that together to write a velocity vector at time is equal to 0 to represent the initial velocity, which is, of course, has direction, theta with respect to the horizontal, and magnitude, which would be the initial speed. To help us do that, let's look at our diagram here. And you can see the green vector, which I will trace again, that represents the initial velocity vector. So theta is the angle with respect to the horizontal, and the magnitude of the initial velocity vector is, of course, the initial speed. So let's construct a triangle here. It's a right triangle that we're constructing. Here's the right angle. And this leg would represent the horizontal, and this length would, this leg here on the side would represent the vertical. So we can write using trigonometry that cosine of the launch angle theta is equal to adjacent over hypotenuse, or x over the magnitude of the velocity vector, and sine of the angle theta, the launch angle theta, is opposite over hypotenuse, where the length of the hypotenuse is the magnitude of the velocity vector. And I can write here xi and yj. So I can solve for x and y in terms of the initial speed, which is the magnitude of the velocity vector at time is equal to 0, and the launch angle theta. So x would be the initial speed, which I can simply write as v naught times cosine of theta, and y would be the initial speed, which I can simply write as v naught times sine of theta. So what that allows me to do is write another initial condition. I can write v naught, the initial velocity, in terms of the launch angle theta, and the initial speed would be x times I plus y times j, where x is the initial speed times cosine of the launch angle, and y is the initial speed times sine of the launch angle. So I have my two initial conditions, and they are related to the initial height h, the launch angle with respect to the horizontal theta, and the initial speed v naught, which is of course the magnitude of the initial velocity. So now let's talk about what's going on after I launch the object in projectile motion. The only force that we're assuming is acting on the object after launch, neglecting air resistance, would be the force due to gravity. And of course, gravity causes the object to accelerate towards the center of the Earth. So now you're going to draw a vector pointing towards the center of the Earth. And I'm not drawing this to scale because obviously the acceleration vector will have a certain magnitude. And that is going to be depending on whether you're using feet per second squared or meters per second squared for the acceleration. But one thing that you should notice is that the acceleration vector only has a vertical component to it, no horizontal component, because acceleration due to the Earth's gravity is causing the object to accelerate towards the center of the Earth. So this is something that we know at the very beginning of the problem, the acceleration due to the Earth's gravity, and there is no horizontal component to it, and there is only a vertical component to it, and it is of course pointing downward, so that's why we have negative g, where g represents the gravitational constant. And if you're using feet per second to measure the acceleration, that would be negative 32 feet per second squared. And if you're using meters, that would be negative 9.8 meters per second squared for acceleration. Or you can just say g is equal to 32 feet per second squared, and g is equal to 9.8 meters per second squared. But of course here you have negative g because acceleration is pointing downwards. So now we're ready to go ahead and do the integration. We can integrate the acceleration vector to get the velocity vector, and we'll have constants of integration that we need to solve for using our initial conditions. And then once we have our velocity vector, we will integrate that to get our position vector, and we can solve for the values of the constants of integration using our initial conditions. And once we have the position vector, we'll be done. That's what we're after. So let's go ahead and take a look at integrating the acceleration vector to get the velocity vector. So we start with the acceleration vector, and note that there is no t here because the force due to the Earth's gravity is constant. It doesn't depend on how long it's been since you launched the projectile. So now we'll go ahead and find the velocity vector by integrating the acceleration vector. And of course, we're going to integrate on a component by component basis. So we integrate the horizontal component of the acceleration vector, and we're going to integrate the vertical component of the acceleration vector. So when you integrate the horizontal component, the integrand is 0, so the antiderivative would be just some constant. So I write c sub 1 I, and when you integrate the vertical component of the acceleration vector, the integrand is a constant. It is negative g, so the antiderivative of that with respect to t would be negative g times t. When you differentiate negative g times t with respect to t, you get negative g, plus a constant of integration, j. So now we have found the velocity vector, but I need to figure out the values of these two constants of integration. So how do we do that? To figure out the values of the constants of integration, I need to use my initial condition for the velocity vector. The initial velocity vector v naught in terms of the launch angle theta and initial speed is here. So we're going to use that. To allow me to use that, I need to go ahead and evaluate my velocity vector at time is equal to 0. So I have v of 0 is equal to, there is no t here, so I just have c sub 1 I. There is a t here, so I substitute 0 for t, so I get 0 plus c sub 2 j. And I'm going to equate that with my initial condition v naught. Since both of these vectors are the same, v naught, they need to be equal, which means their horizontal components have to be equal, and of course their vertical components have to be equal. So that tells me the values of the two constants c sub 1 and c sub 2. So using that, I can write my velocity vector v of t is equal to c sub 1 I, which would be v naught cosine theta I, and negative gt plus c sub 2. And c sub 2 is equal to v naught sine theta j. So now I have the velocity vector, and I'm after the position vector. So I need to integrate the velocity vector to get the position vector, and I will have constants of integration, and I will use my initial condition for the position at launch, the initial height, to solve for the values of those constants of integration. So this is where we are now. We found the velocity vector and we need to find the position vector. One thing that I noticed is that this is supposed to be an r. I either wrote r and it looks very much like a v, or I accidentally wrote v. But that's supposed to be an r for the position vector that we're after. So what we need to do now is we need to integrate the velocity vector that we just found so that we can find our position vector, which will give us the position of our object in projectile motion. So we integrate the velocity vector that we just found to get the position vector. So we're going to integrate the velocity vector on a component by component basis. So this is the horizontal component of the velocity vector, and we're integrating that with respect to t. And then here we have the vertical component of the velocity vector, and we're integrating that with respect to t. So you're integrating with respect to t, and what you'll see here is that there is no t here in v naught times cosine of theta. So those are constants with respect to t. So the antiderivative of this constant with respect to t would be v naught cosine theta times t. And when you take a look over here, of course, we need to have a constant of integration. So I'm going to have to write plus c sub 3. I had used c sub 1 and c sub 2 earlier. So now I use c sub 3. And then for the vertical component, we're going to integrate on a term-by-term basis. Again, we're integrating with respect to t. So what you see here is negative g times t to the first. So the antiderivative will be negative g times t to the second over 2. For this particular term, there is no t. So this is a constant. V naught times sine theta is a constant with respect to t. So you will have for the antiderivative v naught sine theta times t. And then, of course, you will have a constant of integration that we will call c sub 4. So now we need to figure out the values of the constants c sub 3 and c sub 4, and to do so we're going to use our initial height. This was represented earlier as a vector. R of 0 is equal to 0i plus hj, where h is, of course, the initial height. So to be able to use that, we need to evaluate the position vector that we had just found at t is equal to 0. So wherever you see t, you will substitute 0. So when you do that with the horizontal component, you get 0 plus c sub 3 I. When you substitute 0 for t here and here, you will get 0 plus 0 plus c sub 4 j. And equate that with our initial condition r of 0 for the initial height, which is 0i plus hj. And you can see that c sub 3 would have to be equal to 0, and c sub 4 would have to be equal to h. So that gives us our position function for an object in projectile motion. We have r of t is equal to c sub 3 is 0, so for the horizontal component we have v naught times cosine theta times t plus 0 I, and then for the vertical component we will have negative 1/2 gt squared plus v naught sine of theta times t plus c sub 4, which we found to be h plus hj. So we have just derived the position vector for an object in projectile motion, and you can see that it is in terms of the initial height, the launch angle, and the initial speed at which the projectile is launched, and this will tell you the position of the object in the plane of its motion as a function of time since it was launched. Usually this particular, the vertical component of the position, we usually write the terms in a different order, writing this term first and this term last. So we have just found what we're looking for. We now have a position vector that will tell us where the projectile is in the plane of its motion t seconds after it was launched, with reference to the coordinate system that you see drawn here against the picture. So what is the position vector that we found? It is r of t is equal to v naught times cosine of theta, and v naught is the initial speed, and theta is the angle from which the projectile was launched, times t times the standard unit vector I, plus h, which is the height from which the projectile was launched, times v naught, the initial speed, times sine of the launch angle theta, times t minus 1/2 g t squared, where g is the gravitational constant, and if you're measuring acceleration in feet per second squared, g would be 32 feet per second squared, and if you're measuring acceleration in meters per second squared, g would be 9.8 meters per second squared. That's what we were looking for, and we have derived the position function for an object in projectile motion in terms of its initial height, its initial speed, and launch angle. So in our lesson today, we looked at an object that was launched from an initial height with an initial speed and angle of elevation, and we looked at how we come up with Theorem 12.3. You understood how the position vector for an object in projectile motion is derived from the acceleration vector. We know this because the only assumption that we're making is that there is no other force acting on the object after launch except the force due to gravity, and we know the acceleration vector due to gravity. You will understand that the position vector for an object in projectile motion will tell you the position of the projectile at time t since the object was launched, and that is right here, and this is what we discussed. Neglecting air resistance, the path of a projectile launched from an initial height h with an initial speed v naught, an angle of elevation theta with respect to the horizontal, is described by this vector function that we derived from the acceleration vector due to the force of gravity, where g is the gravitational constant.